Hi guys, this is the video on the section 10.7, the chi-square test for association. So this is very similar to the section 10.6 on the chi-square distribution test for goodness of fit. The emphasis here though is on association, so a little bit different, at least in terms of how we build the hypotheses. Otherwise, everything else that we talked about in section 10.6 is pretty much the same for the computation. This one can get a little tedious as well, in just like we noticed in section 10.6, but again, a lot of the stuff is pretty similar. So once again, what you should notice is that we've got a set of conditions that the section begins with. The book emphasizes these, so that is important, so make sure you take a read there. The biggest thing with this type of test is that we're dealing with categorical variables. That's what association in this respect is referring to. So trying to compare categorical variables, is there a relationship? That's what it's really asking. So it says, when using the chi-square test for association, the two variables in the population need not be numerical, nor does the relationship need to be linear. So that's a very cool idea. This idea of linear relationship is actually explored in chapter 12. So, for instance, we could examine whether there is a dependent relationship between gender and choice of car color. So, in the calculation of the test statistic for the chi-square test for association, here we go. We use observed frequencies for every possible outcome, which are themselves numerical. So there's that word, observed frequencies. And of course, expected frequency. So that comes back to us again. What I also want to draw attention to, hopefully you've noticed, is we've got our 5 steps to the hypothesis test. That has not changed. Okay, and again, we've got some a little bit of a different process than we saw in sections 10.1, 10.2, and 10.4, but ultimately still the same process. Now, the null and alternative hypotheses for the chi-square test for association, I want you to pay careful attention to these because there's only one form that the hypotheses take, which is nice and easy, okay? And so the form that they take, the null, is that the two variables in the population are independent, and the second one here is for the alternative is the two variables in the population are not independent. And so there's another way you can frame it. So when you say that the two variables in the population are are independent, this means that they are not associated. Okay, and if we're saying that they're not independent, it hints that they possibly are associated in some way. So you might see that word association or associated used instead of independent or not independent in some textbooks that you might look at. But again, this is the only form that the hypotheses take. Nice and easy. Now, we've got something to look at here that we consider a two-way table. So if you're following along in those guided notes, I think you got to write in the piece for the hypotheses here, which again are stated, but also anything here that's bolded is something you have to also fill in. And so when we consider a hypothesis test in chi-square test for association, we're given a two-way table. Now, if you remember from 10.6, we had a frequency distribution. So if you're looking to say, okay, what's the difference between 10.6 and 10.7? 10.6, we have a frequency distribution. In 10.7, we have something called a two-way table. Why is it a two-way table? Well, it's a two-way table because we're looking at two variables. We call it a row variable, and we call it a column variable. Okay. So in our case, in this particular one, we're looking at admission numbers to a particular program. Notice that word, it's observed. That means somebody actually went and collected this data. So in this case, they're counts. Now the two-way table rather, we have column variables. The column variables are male and female, in other words, gender. And then we have admit and deny, which is the admission status. And so that would be considered the row variables. So that's why we have two-way table. Now, you'll notice that there are some values here that are in red and they're bolded, and that's what you would be filling in on your guided notes. So it says the tables and the value represent what are called frequencies. Okay, we've seen that before. So they are counts. Okay. And so what they represent in our case literally are really two things, okay? And since they're representing two things, we call it a joint frequency. So there's another vocabulary word. So for example, if you take the number 40, it represents 40 females who were denied, okay? And so that's considered a joint frequency. Now the other one here that it talks about deals with the total. So we've got a total column and a total row. These are called marginal frequencies, okay, because they are in the margin. Now you notice there's a number here that got circled twice, the 140. That's going to represent for you the total number of male and females that are actually have been observed, okay? And that should make sense because if you add it any way you go, 55 and 85 or 80 and 60, we get 140, okay? All right. Now, this chapter examines the relationships between categorical variables. And so that's another clue that kind of separates this from sections 10.6, where we're now dealing with categorical variables, right? Gender and admission status are indeed categories. Okay, so what do we use this for? Well, using the table above, we could study whether gender is related to admission status. And so that certainly is a question that maybe somebody wants to research, okay? So that is, put another way, does being male or female play a role in whether someone is admitted? Or put even more plainly, does gender discrimination exist? And so we do have some faculty here at Wayne State, for example, who are interested in studying such things as gender discrimination or just discrimination in general. So looking at the proportion of men who were admitted, we have that 35 over 80, or 44%. And for women, we have 33% who were admitted. So looking at the raw data, right, it suggests that something is amiss, something is off. So the question is, how do we study it? And the example, again, or the answer is back to hypothesis testing. Okay, so let's look at the context of this example. So we turn to the hypotheses. So we're going to study gender and admission status. So if you look at the null, it says there is no association, right? So that's, in other words, saying that these two variables, these two things are independent. So remember, you can either use the word independent, right? Gender and admission status are independent, or you can say there is no association between the two. Either way is fine. And for the alternative, we say there is some association between gender and admission status, which indicates or suggests to us that these are dependent or not independent, right? Some sort of relationship exists. Okay, now what we have to look at and establish again is the expected count. Now you should remember from section 10.6, okay, we had that formula NP, if you guys remember that. Well, this is section 10.7, so we don't use N times P because that dealt with probabilities. We're not dealing with probabilities here. This is the formula that we use for section 10.7. And so what you do is you take the row total and you multiply by the column total and you divide that by the table total. So what the heck is it saying? Well, if you notice, this particular table here, this is for the observed counts, okay? If I were to delete the total columns and rows, you'll notice that you only have 4 cells, right? Male who were admitted, male who were denied, female admit, and female deny. You'll notice that those translate nicely, those 4 cells, to this table down here, which is dealing with the expected counts. And so to get the expected counts, what you have to do is deal with the formula up here. Okay, so what we would say then is that this is actually a 2 by 2 table, and the reason it's 2 by 2 is it's 2 rows, 2 columns. Okay, so when you consider how big the table is, you ignore the totals. Okay, all right, now we need to see the totals, so let me get rid of my markings here. There we go. Okay, so to run this formula, let's do male who were denied. Okay, so to do that, what we have to do is we have to look for the row total for the denied. Okay, so the row total for denied, here's denied, and the row total is 85. So we take 85 times, and then we have to do the column total. Well, the column total for males is 80. So that's going to be 85 times 80 divided by the table total, which was 140. And so when we multiply that out, you see we get 48.57. And so you have to do that for each of the cells in the table. Okay, so that's a total of 4 times. So a little bit more cumbersome than section 10.6, maybe a little easier depending. And so then what we get are these decimal values. These are called the expected frequencies, guys. Those are the expected frequencies. Remember, these in this table here are the observed. Okay? So that's the sort of the first piece to this, is computing the expected values. And it's very important that they match, right? So this number 35 here, its expected count is 31.43, etc. Okay, so the observed count of 40, its expected here is 36.43. Okay, now what we have to do is we have to actually do the computation for this statistic. And so there's the formula again. That should look very familiar. I think the one in section 10.6 was the observed minus the expected all squared over the expected. It's the same formula. So that's the good news. That doesn't change. Now, what I offer here is an alternative for its computation, and this is the table method. Now, if you remember in 10.6, what we did is we actually computed it out the long way, where we built fractions that were based on this formula. So if you'll permit me, let me show you an alternative, which is the table method. And so if you're comfortable with the other way, then use the other way, that's fine, but there is an alternative. Okay, so the first thing to do, First thing to do is in the chart, we want to write down the observed and the expected. So the observed, again, are going to come from the table that was originally given here. Okay, and so that involves, let me get rid of these other lines here. And so that's going to involve the 4 values that are listed here, right? So 35, 45, 20, and 40. And so those are listed very carefully in the chart here. Now, where the tricky part comes in is you got to make sure that you list the expected count, but it's got to be partnered with the correct observed count, okay? And so this is where sort of the position in the chart matters. Let me show you what I'm talking about here without getting too much off topic. So does everybody see how we have male and admit, its expected count is here, and male and admit's observed count is here. You notice that's the top left corner, right, for both pieces of the table. So you'll notice on the chart below that those 2 values are indeed matched. And so you have to kind of take that process as you proceed, and you have to fill them in. Okay. Now the next part to the process is I'm actually going to work the numerator of the computation, okay? And so that means we have to take the observed minus the expected. So I'm working on the numerator here. And so you do that, okay? So you take each observed and you subtract, and if you did it right, you should get a sum of 0. That's how you know you did it right. Now, if you remember back to the computation for standard deviation back in chapter 3, remember we can't have this negative. So what we do to sort of reverse that effect is just square it. And so that's what we do here. We square it. So we get 12.7449 for each of them. Now what you should notice is that's the entire numerator. And then the second step, what we do is we divide by the expected. Okay, so you got to make sure you're reading the expected values very, very carefully. So for example, in this first one, what you're going to do is 12.7449, and you're going to divide by 31.43. Then you're going to do 12.7449 divided by 48.57, and that's what gives you these values here. Sigma tells us to sum, and so we get a test statistic value of 1.5584. So once again, that sum represents the value of this test statistic, and we have to compare that rather with the critical value. And so remember, the critical value, that comes from the chart, right? Okay. And so in order to read things off of the chart, what we have to do is we need our degrees of freedom. So hopefully you remember with the chi-square distribution, we have to use this degrees of freedom. Now, we had a different formula for the degrees of freedom in the last section. So if you remember section 10.6, its degrees of freedom formula was k minus 1, and k was the number of outcomes. Well, we're not in 10.6. The degrees of freedom formula here is the number of rows minus 1 times the number of columns minus 1. So it's a little multiplication problem. Okay, so R is the number of rows, and C is equal to the number of columns. Okay, so in our case, we have to determine how many rows and how many columns we have. Okay, well, this isn't so bad. Now we have to be careful again, because I warned you guys that we cannot count the total row and total column when we're trying to determine how many rows and columns we have. Okay, that was a lot to say, so let me go back up here. Okay, do you remember how I said that this was indeed a 2 by 2 table, right? I made that indication on this side. We said it was a 2 by 2 table, and the reason for that is if you exclude the total column and the total row, that only gives us 2 columns and 2 rows. So this tells me that we have 2 rows and 2 columns. So the computation for the degrees of freedom then, in this case, is very simply going to be 2 minus 1 times 2 minus 1, or 1 times 1, which is 1. So not a very exciting degree of freedom, but you can see that if we had a table that was much larger, the computation would be quite a bit. Okay, and so on a quiz or a test or homework, we could give you a larger chart and ask you just to compute the degrees of freedom, and that's not bad, right? You just got to make sure you count the number of rows and columns. But to run the computation for the test statistic, my goodness, this chart here would be very, very large. So we have to be careful. Okay, so what we do is we've got our degree of freedom, and we again return to the same chi-square distribution chart that we had before. So here's the degree of freedom that we're dealing with, which is 1. Okay, and I think for this particular test, we're going to look at alpha is 0.05, and so that's going to give us a value that's 3.841 as the critical value for this particular test. Okay. And there was the computation. Okay, so we know then that our test statistic that was computed was 1.5584. Okay, we go to our table with alpha is 0.05 with 1 degree of freedom, and we found that the value of the critical value was 3.84. So again, remember, we always compare the chi-square statistic versus the chi-square critical value. Okay, and so in this case, since the statistic is less than the critical value, this means we have to accept the null. Okay, accept the null. So put another way, we fail to reject the null. Okay, so those conditions we looked at before about the decisions back in section 10.6 are still the same. Okay, so that's nice. There's some consistency between those two sections. Now, what follows are some cautions about the chi-square test. So there is some danger. I do want to talk for just a moment. And where those changes can come in is how you define the categories. Okay, and so there is some danger. You have to be careful. So this example talks about religion, for example, and how you classify different religions can make a difference in this test. And then there's this third one here that talks about an association or comparison that holds for all or several groups can actually disappear or reverse direction when the data is combined or formed into a single group, and it's known as Simpson's paradox. So there are some issues that can certainly come up in a chi-square test. And so really the important thing is how we decide to classify the variables. And so there is some trick to it. So if you're ever going to use this test, make sure you do some consultation. And so we've got some other examples that will follow in the notes, and so I would encourage you to certainly give those a try.